So this is Jeff Hamrick again at the Financial Analysis Program at the University of San Francisco. I want to spend a minute or two talking about how we use a table of Durbin-Watson critical values to make a statistical decision after we've computed a Durbin-Watson test statistic using Stata. So there are statistics textbooks everywhere that have various versions of these Durbin-Watson significance tables in them. This is one particular set I've snagged off the internet. They all basically look the same, but you need to be aware of the following issues when you use these tables, because there are a number of moving parts with Durbin-Watson significance tables. The first is you'd ideally like to be reassured from some information in the table that it has been built for models with an intercept. Technically, the classical Durbin-Watson test requires not only that you not have a lagged version of the dependent variable as an independent variable, but that you also have a model with an intercept term in it. Okay, and then you want to find out if the columns here, and you can see that the columns are associated with k equals 1, k equals 2, k equals 3, k equals 4. You want to find out if that includes the intercept or excludes the intercept. It's a pretty strong hint because we see k equals 1 right here, that because we don't regress against constant terms, we regress at a minimum against a constant term plus one slope. That's what simple linear regression is, after all. That probably what this significance table is implying is that k is the number of parameters we have to estimate above and beyond the intercept. And indeed, when you look at the footnote down here, that's exactly what you see. So in the example that we just did with the electricity bill, we had 6 parameters in total that we estimated, one of which was the intercept, and 5 of which were slope coefficients. So we're going to focus in on k equals 5 using this particular table. And I'm going to try to pick a number of observations that's roughly the same as, I'm going to try to choose a row here that corresponds to our number of observations. Now we had 118 observations in the last example. None of these are going to match that exactly, so I'm going to go on ahead and choose, like, let's say 100. There's not a huge difference in k equals 5 between 100 and 150, but if my Durbin-Watson statistic were around any of these 4 values right here, I would want to be a little bit more careful. As it turns out, it's not the case. Okay, so what I look here, if I'm using row 100, I look for this lower cutoff DL and this upper cutoff DU, and I see that the lower cutoff is 1.441 and the upper cutoff is 1.647. Since my Durbin-Watson test statistic was 0.88, and that is definitely lower than the lower cutoff of 1.441, I'm going to reject the null hypothesis of no serial correlation of order 1 in this particular model. If the Durbin-Watson test statistic we had obtained was between 1.441 and 1.647, we would not be able to make a decision. And if it were greater than 1.647, we would not reject the null hypothesis. So what we're really looking here to do, if we're going to reject the null hypothesis, is to have a Durbin-Watson statistic that's less than this lower value of 1.441. Okay? Now, you have to do something slightly different with these charts when you want to test for negative serial correlation, which I've indicated to you is pretty rare. The easiest thing to do is to take your Durbin-Watson statistic and to subtract it from 4. So since our Durbin-Watson statistic was about 0.88, 4 minus 0.88 is 3.12. 3.12 does not come nearly close enough to being underneath this lower threshold of 1.441. So we would not detect negative serial correlation there either. We never really suspected that that was going to be the case for the electric bill model because our Durbin-Watson statistic was 0.88, and 0.88 is less than 2, and that's indicative of the possibility that we might have positive serial correlation, and so we generally speaking just wouldn't even worry about checking for negative serial correlation in a formal statistical sense. So in most financial models and models in economics, positive serial correlation is the problem. So you rarely have to worry about doing that flip to check for negative serial correlation. Anyway, this is how you use a Durbin-Watson table. It takes a little bit of practice to get comfortable with it. This is how you use a Durbin-Watson table to make a statistical decision after you compute your Durbin-Watson test statistic in Stata.